Hello chemists, this is Ms. Bluchino and you're watching lesson 5.5 on predicting the products of double replacement reactions. Today we're really just going to focus on how to look at the reactants in a double replacement and accurately predict the formulas of the products along with their solubility. This is hands down the most involved lesson of this unit. So goals for today. We're going to be able to dissociate ionic compounds into ions. Dissociate just means break apart. This is a big deal because this happens every double replacement reaction. We then need to recombine those ions and predict the formula of the products. Also a really big deal. Recombination to predict products is how we get the right side of the reaction. And finally, we're going to use table F in our reference table to determine the solubility of an ionic compound. Lots to do. Let's get started. Many times in a double replacement reaction, we're working with aqueous reactants. Just to remind you what aqueous means, we would take our solid, we dissolve it in water, and we'd either stir it up or just give it time to become a homogeneous mixture. That's what aqueous means, dissolved in water. Double replacement reactions often have ionic compounds as the reactants. When ionic compounds are dissolved in water, they don't just get wet the way sugar, a covalently bonded molecule, would. There's more going on, and I've got a quick video that I'd like to show you about that.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution.
Let's stop it there for just a second. Yeah, so it's kind of crazy what's happening when you take something like salt and you dissolve it in water. The water molecules attack that really organized crystal lattice, that big structure of repeating cations and anions, and start to drag the ions, off into solution. So the attractive forces between those cations and anions, it's not strong enough to overcome the attractive force between the water molecules and the cation, or the water molecules and the anion. So as water dissolves salt, we're creating these ions that are just floating around in solution. And it's those free-floating ions that are able to react with one another when we combine them with another aqueous solution and potentially get a double replacement reaction to occur. Let's try to apply that to a chemical equation. All right, so we're going to start by writing dissociation equations. And just to clear up some terminology, when a soluble ionic compound is dissolved. So a compound that is soluble will dissolve in water. For example, like oil doesn't dissolve in water. We'd say it's insoluble. When a soluble ionic compound is dissolved, it will dissociate or break apart into ions. So let's look at this change. In this case, we have calcium chloride, a solid. Water over the reaction arrow just means it's dissolving. It's not really a reaction between the two. So I'm going to break calcium chloride up into calciums and chlorines. The challenging part is trying to figure out the charge of the calcium ion and the charge of the chloride ion. You can use your reference table to help with this. You also know that the subscript of the anion is related to the charge of the cation and vice versa. So whether I use the reverse criss-cross method or I check the periodic table, I know that calcium is going to be a +2 charged ion, and it's going to be aqueous because it's now dissolved in water. Let's say I had a subscript of 1, basically. I know that chlorine is going to have to be the negatively charged ion, so the chloride ion must have a charge of -, and it will also be aqueous. If I wanted to get this balanced, I see that I've got 2 chlorines on the reactant side. I could put a coefficient of 2 in front of the chloride ions to balance it out. I'll be honest, at this point in the game, I'm really more concerned with you breaking it up into ions. I've found that with a lot of new chemists, when they start putting the coefficients in here to balance the equation, when we go to recombine ions and predict products of the double replacement, things get really messy. So this is not balanced right now, but please leave it as is so we can really focus on the charge of each of the ions. And again, just kind of a reminder of the reverse criss-cross method. Let's try some of these out on your own. So I've got these 3 problems. I'd like you to predict the ions that will form. I'm going to walk through number 1. If you think you got it, just pause me or I guess ignore me. And if you want to try them on your own, pause and work on them. All right, so the first one we have is Na2S, sodium sulfide. I know I'm going to make sodium ions. I know they'll be aqueous. And I'm going to make sulfide ions. They'll also be aqueous. I know that the subscript of the cation is related to the charge of the anion, and vice versa. I could also check the reference table and see that sodium ions are always positively charged. Might be a little bit more confusing with sulfur as it's got multiple oxidation states listed. But as an ion, it's got to be negative, so it must be the -2 charge. Pause me, try these out, and check your answers when you're finished. Be careful with questions 2 and 3. They are more challenging than the 2 we've done so far. Potassium phosphate. What I see so many students do, they correctly get the charge of phosphate, and then they decide, oh, this 4, that must have been from potassium. Use your reference table. PO4 is phosphate when it has a charge of -3. There is no additional subscripts. If there were, then there'd be parentheses around the phosphate. So don't fall into that trap. Potassium is not a +4 ion, it is just +1. And you can imagine that a lot of people make the mistake of saying iron is +1 and sulfate is -1 since there are no subscripts. Consult the reference table. You're going to get sick of hearing me say that this lesson. It's iron 2+ and sulfate 2-. Those are the ions that will form when I take those 3 compounds and I dissolve them in water. That's the first step of our double replacement reactions, is to break apart the ions into the aqueous solutions. In a double replacement reaction, we'll take 2 solutions of aqueous ions and we'll mix them together. And sometimes you end up producing a precipitate. You form ionic compounds. So let's talk about how to do that. So we're going to combine our 2 solutions of aqueous ionic compounds. And we can predict the formulas of the products that will form using the criss-cross method, basically just the reverse of what we did with dissociation. So let's look at this example. Let's say you've got silver ions and sulfide ions floating around in solution. I can predict the formula of silver sulfide. Technically that's a 1, just using the criss-cross method. So if silver plus and sulfide 2- ions are in the same general area, I'm going to make silver sulfide, which is a solid. And we'll talk about how I know it's a solid once we get finished predicting the formulas. Try some out. Ooh, I have a typo there. It'd be NO3-, my mistake. All right, we have done the criss-cross method before, so my recommendation is to pause me, try these out, and check your work when you're finished. Check your work, see how you did. We have lead reacting with nitrate. We'll make lead 2 nitrate, Pb, NO3 in parentheses, 2. Barium and sulfate, when they combine, those charges will cancel. Just for BaSO4, no subscripts of 2. And last, we've got calcium reacting with hydroxide to form calcium hydroxide. Make sure you've got the parentheses around hydroxide and the subscript of 2. There's a real common tendency for students to forget the parentheses and just make it CaOH2. And then instead of 2 hydroxides, it's 2 hydrogens, and that's incorrect. These are the 2 big pieces of predicting the products of a double replacement reaction. Take the reactants, dissociate them, and then recombine the ions, use the criss-cross method to predict the formulas of the products that will form. The last little piece is determining solubility, deciding will this substance stay as aqueous ions in solution, or will it form a solid and will observe a precipitate. So we're going to describe our ionic compounds as either being soluble, which means able to dissolve in water, insoluble, unable to dissolve in water, and we've also got something that I'm going to call slightly soluble, where it's going to dissolve in water to a small extent. Not all compounds are equally soluble. If you want to take AP chemistry, you'll be able to calculate solubility product constants, and you'll have like numbers attached to solubility, but this is what we've got for intro chem. We know in a double replacement reaction, we're going to form a precipitate. So we're going to look for the production of an insoluble solid. And table F is the key to predicting solubility for ionic compounds. So if you got your reference table, open it up, take a look at table F. Here's what table F looks like. It is a really important table used for double replacement reactions. All the way over on the left, we have ions that form soluble compounds. So these are ions that usually when they're present in a compound, that compound will be soluble or will dissolve in water. So for example, anytime we've got a group 1 ion, lithium, sodium, potassium, rubidium, etc., odds are that's going to be a soluble compound. Same with ammonium, nitrate, so on and so forth. I know you can read. We have some exceptions when we start looking at the halides. So the halogen group, when they form ions, are called halides, chloride, bromide, and iodide. They're generally soluble unless they're combined with silver, lead, or dimercury ions. In that case, they will form an insoluble compound. So over the top of exceptions, might as well write insoluble. Now, two big groups of exceptions to know for soluble compounds are your halides and your sulfates. If we move over to the other side of the table, we've got ions that generally form insoluble compounds. Carbonates, chromates, phosphates, sulfides, and hydroxides typically don't dissolve in water when they're in a compound. If you look at the exceptions, they're generally group 1 and ammonium, which are like always soluble. So I like to think of the exceptions as being slightly soluble. That's what SS stands for here. And these are going to be compounds that tend to have pretty low solubility in water. I'm talking about insoluble, and slightly soluble is somewhere in between, doesn't dissolve and dissolves pretty readily. So if I had something like calcium chromate, for example, that's going to be a slightly soluble compound. Sometimes our slightly solubles will be the ones that show up as the precipitate in a double replacement reaction. All right, let's try to put all of this together. So we know in a double replacement reaction, we need to dissociate the reactants and then recombine the cations with anions to form products. Let's walk through one together. Let's take the reaction between PbNO32, lead 2 nitrate, and Ki, potassium iodide. You're being told that they're both aqueous to begin with. First order of business is to dissociate the reactants. I'm just going to draw these little arrows. I know I'm going to make lead ions, and I'm going to make nitrate ions. And with potassium iodide, I'll make potassium and iodide ions. Tricky part is knowing the charge. So I can use the reverse criss-cross method and kind of double check with the reference table. I should be able to determine that lead has a charge of 2+. For your polyatomics, you can go right to table E and look up those. Nitrate has a charge of -1. They're in a 1-to-1 ratio here, but let's double check and make sure that subscripts didn't just cancel out. Potassium is a group 1 metal, so it'll be K+. Iodine, a halogen, will form a -1 ion. All right, so we've taken care of dissociating the reactants. We got to combine cations with anions. Okay, so I know that got to kind of pair them up so they're not reacting with the ion of the same charge and they're not reacting with the ion they've already reacted with. I think this is the easier of the two to take care of, potassium and nitrate. I have +1 for potassium, -1 for nitrate. We always write the metal first, KNO3. All right, I'll take my lead 2+ ion and my iodine -1 ion. So this charge of the lead ion, 2, will become the subscript of the iodide ion. PbI2. Here we go. So now I've recombined and I've predicted my products. Let's get it balanced. Got 2 iodines, only 1 iodine. Let's put a 2 in front of the Ki. All right, now I need 2 potassiums. Okay, 2 potassiums on the product side. I've got 2 nitrates on the product side. Oh, perfect, 2 nitrates on the product side. This is balanced. Last thing I need to do is figure out which of those 2 is going to be the solid. So I'm going to go back to table F real quick. Guess we'll just leave it like that. Okay, so I've got KNO3, I'll just write them here, and I've got PbI2. I think it's easiest to search by anion, since with the exception of group 1 ions and NH4, ammonium, everything is an anion. So there's nitrates. Nitrates, always soluble. Okay, so this is probably not the insoluble product. It's not my precipitate. Let's double check just to make sure that we do have a reaction. Halides, iodides, usually soluble, unless they're combined with, there's lead. This is going to be the insoluble precipitate that forms. So just to wrap this up, KNO3, that's going to remain aqueous. The potassium and nitrate ions are just going to stay floating in solution uncombined. And lead 2 iodide will be my solid. So it's going to be the thing that is the precipitate. It crashes out of the solution and it's going to collect at the bottom of the reaction vessel if you give it enough time. And we've seen this reaction. Lead 2 iodide is a yellow solid. This is tricky. It takes practice, it takes a lot of just kind of walking through it, and don't be shy about kind of showing your work here. As you get more proficient, you can probably skip out on it, but you're going to want to get some repetition in. I'm going to go through one practice problem with you, since again, this is difficult stuff. Okay, so here we are in the practice problem section. Let's take a look at number 4. Ooh. There we go, number 4. So we've got sodium phosphate reacting with magnesium sulfate. First order of business, dissociate into ions. So I'm going to show all of my work. I know I'm going to make, I guess I just gave that away, sodium ions and phosphate ions. I'm going to make magnesium ions and sulfate ions. You might have started to kind of accidentally memorizing the charges of different ions. Sodium, for example, it's a group 1 metal, it will always be a +1. I needed 3 sodium, so phosphate must have a charge of 3-. And if you check table E in the reference table, you can verify that. Magnesium sulfate. Careful, there are no additional subscripts, so there's a tendency for students just to assign a +1 and -1 charge to magnesium and sulfate respectively. But magnesium is a group 2 metal, so it will lose its 2 valence electrons to become a +2 ion. Sulfate, if you were to check the reference table, has a charge of -2. Let's pair them up. Opposite anion and cation will pair. Let's look at the Na and SO4 combining. So I can use the criss-cross method. I can make 2 a subscript for sodium, SO4, sodium sulfate. All right, magnesium phosphate, Mg +2 phosphate -3. I'll use the criss-cross method to get Mg3, PO4, put that in parentheses, get out of the way, 2. This definitely isn't balanced. I'm going to start with sodium. So I've got 3 sodiums on the reactant side, 2 on the product side. So we need to get to a multiple of 6. Let's put a 2 there and a 3 there. 2 phosphates. Okay, 2 phosphates. 3 sulfates. I need a 3 over there. 3 sulfates. And I think that should do it. Yeah, 3 magnesium, so that's finished. Up in the directions, it says just to put a box around the insoluble compound. So we've got to figure out which of those 2 will not dissolve in water. I'm going to scroll up to table F. I've got sodium sulfate. Sulfates, usually soluble, silver, calcium, strontium, barium, lead. Okay, so it looks like sodium sulfate will dissolve without a problem. Phosphates. Phosphates are usually insoluble. Let's see if magnesium's an exception. It is not. It's group 2, and it's obviously not ammonium. So magnesium phosphate is going to be my insoluble compound. Put a box around it. Technically, it would have the little parentheses S after it to represent its phase. So these questions take a little while. You definitely want to practice trying to predict the products. It's not too difficult once you get the hang of it, but it does, like everything else, require repetition. All right, I think that wraps it up for today. Thank you so much for tuning in, and I hope you found this helpful.